Hello everybody. So I'm here with another example of state space for a 2 degree of freedom system. So clearly this is a 2 degree of freedom system where we have two masses coupled together, right? And I want to show you how we can use the state space form and get these matrices A, B, C, and D. And remember, once you have A, B, C, and D determined, then you can easily use Matlab Simulink toolbox and then specifically the state space box to get the output graphically. So here we have these two masses, 2 kilogram mass and a 4 kilogram mass, connected to these springs and damper, and then under the action of an input f of t. So there is only one input f of t here. Okay, and remember input is the u, so f of t happens to be the u. And u, since there is one input, u is going to be a 1 by 1 vector. Okay. So now, first I try to draw the free body diagram and get the equation of motion. So I have the free body diagram of the 2 kilogram mass and the 4 kilogram mass. Here I assume that S is larger than Z. So by that, if I start actually with this free body diagram of the 2 kilogram, since S is going to be larger than Z, eventually the force of this spring with the stiffness of 8 is going to be 8 times the difference between the displacement of S and Z, right? And similarly for the damper would be the relative velocity times the damping constant, 4. Once you determine the direction of these forces acting on the 2 kilogram, then you have exactly the same forces, action, reaction in the opposite direction. And then of course the force of the spring here is going to be just 6 times Z. Okay, and then you have the f of t here. Go ahead and write the equation of motion, which is F equal ma for each one of these. So for the 2 kilogram mass, taking this direction to be positive, these two forces then are negative, and then you have F of t as positive, equal to mass times acceleration. By the way, if you're wondering why I use S and Z, I didn't want to use like x1 or x2, because they're going to get mixed up with the x here for the state variable, state space variable here, or state space vector. Okay, similarly for the 4 kilogram mass, if you look at the free body diagram of it, these two forces are going to be positive, these two, so positive, positive, and then minus 6z is going to be negative, equal mass times acceleration of that guy, z double dot. Now remember that in the previous example on the state space, I said that actually you want to keep the second derivative or the highest derivative on one side and then move everything to the other side. And then I am going to actually normalize this and give you the final outcome. So divide by 2 here and divide by 4 here. And then once you divide by 4 here, you have to divide everything by 4. So it gets cleaned up and simplified in this form. So S double dot becomes minus 4S plus 4Z and so on. And you see how when we divide by 2, f of t is divided by 2, so we end up getting 1/2 of f of t. Similarly for the second equation, after you divide by 4 here, you end up getting this. Let's move to the next page. Now, actually, before we move to the next page, you notice that this is the form that we want our state space to be. And our objective is to find these matrices. And once we have the matrices A, B, C, and D, right, then we are ready to simulate this using Matlab. And that's my plan, by the way. I want to show you how easy it is actually to use the state space to do this. All right. Let's go to the next page. I rewrote these two equations for you. And remember, u is just, there's only one input here, f of t. Now you could have multiple input, by the way. You could have another input that is acting on this force, on this mass rather. So it all depends on how many inputs you have. And that determines the size of the vector u. Anyway, so we want to get this first. The x dot equal ax plus bu. All right, so how many state variable we have? What size is our state vector? So remember, for every second order you know, term here, which is s double dot, we're going to have two state variable. So we have two of these, therefore we're going to have four of them, x1, x2, x3, x4. And this is how I did it. So x1 is going to be what? S. Remember, x2 would be always the derivative of that, s dot. x3 would be z, and x4 would be z dot. So now we have to work on this guy, x dot. So just take the derivative of this. So x1 dot becomes s dot, which is actually x2. x2 dot is s double dot, which is equal to minus 4s. Well, what is 4s? S is what? S is x1. See that? Plus 4z. What is z? Z is x3, so it becomes 4x3. Minus 2s dot. What is s dot? x2. And so on. 2z dot plus 2x4 plus, instead of f of t, I just put u here. All right. What is x dot 3? It becomes z dot. What is z dot? Z dot is x4, right? Here we go. And x dot 4 is z double dot. And what is z double dot? Z double dot is, right? Just put this back on. Z double dot is right here. Is 2s. What is s? x1. Minus 3.5 z. What is z? x3, right? Plus s dot. What is s dot? x2. Here we go. Minus z dot. What is z dot? x4. See that? Very easy. All right. So now we want to put this in the matrix form. X dot, the derivative vector, is equal to a times x. Now remember, x is established already, is a 4 by 1, right? X is established as a 4 by 1. So this is how you figure out the size of your A matrix. You see, we already know that x dot vector is 4 by 1. So this must be a 4 by 4. Because remember, these two numbers have to match, and then the outcome is 4 by 1, right? So let's go ahead and figure out what the outcome is going to be. All right, I mean for matrix A. So here we start here, we say, okay, x dot 1 is x2. No x1, 1 x2, no x3, no x4. And similarly, minus 4, minus 2 in order. 4 and 2. Yeah, x1, x2, x3, x4. What about this third one? This guy, which is this one. No x1, no x2, no x3, 1 x4, 0, 0, 0, 1. And similarly, 2, a 1, negative 3 and 0.5, and a negative 1. Here we go. And then what about our input? So remember, u is a 1 by 1. So what do we need this to be? We need this to be a 4 by 1. Again, 1 and 1 match. And the outcome is 4 by 1, which is what we need here. Right? And just look at the equation. In this equation, there is no u, 0. In this equation, there is a 1/2 u, so 1/2, nothing here, and nothing here, 0 and 0. Okay, next. How about the output? Output, remember, is in this form, y equals cx plus du. Now, it depends on what you want the output to be. Usually, you want the output to be displacement of the two masses, meaning s and z. Remember, S and Z represent what? The displacement of mass, the 2 kilogram and 4 kilogram masses, right? So therefore, our output is going to have two items in it. So it's going to be a 2 by 1, right? It's going to be a 2 by 1. So Y1 we want to be S, the displacement of the one of the masses, and then the other one is Z. But remember, S is what? S is X1, right? And Z is what? X3. So we want eventually X1 and X3. All right, so we write the equation again. This is this guy. This is C matrix. This is your X. Again, remember, X is what? Already predetermined. It's 4 by 1. We have no choice on that. All right, so therefore we can figure out the size again. You see, remember, Y1, Y2 is a 2 by 1 vector. Therefore, we need a 2 by 4 here. So you see, this is a 2 by 4 C matrix, because again, 4 and 4 match, and we get 2 by 1. So now we want y1 to be what? Y1 to be x. So 1x, x1 rather, 1x1, nothing, x2, nothing, x3, and x4. And then we want y2 to be what? Z. What is z? x3. So 0, 0, 1. 1x3, right? And 0x4. So now let's take a look at D. What is the size of D? There was a pause there, guys. I apologize again. Every time I touch this iPad, it stops because of this app. Anyways, D is gotta be a 2 by 1 because 1 and 1 match here, and we have a 2 by 1, and that matches what we want here. And as I said, D called direct transmission matrix, and is always 0 for the type of problems that we do. So what I will do, this would be the last video, guys, for this course. What I will do, I want to show you a simulation of this, which I'm going to use probably either a Zoom lecture or a Panapto lecture to show you what's going on. Okay, so stay tuned, guys, for a video of either Zoom or Panapto. As always, thanks for watching and listening.